Hello, BC Calculus students. This is Mr. Johnson, and we are beginning Chapter 8, which is on sequences and series. And 8.1 is on sequences, and this is something that you have probably seen before in honors pre-calculus, but it's probably been quite a while. And so I'm going to start assuming that you don't remember anything, or at least just start so that we're all on the same page with regard to what a sequence actually is. Some of the initial stuff is going to be a little bit easier to deal with, and it will get difficult pretty quickly for most of you. And so I'll try to work at a nice pace for you, but I'll take this section and break it into a couple different videos just to make it a little more manageable. So first of all, a sequence is a list of numbers, and that's key to the distinguishing factor between sequences and series. A series is the sum of numbers of a list. And so this is just simply a list of numbers. And it's written, you can see a sub 1, a sub 2, a sub 3, and so on. And it has a domain that is a set of positive integers. So when we look at this particular sequence, we're looking at the first term of the sequence. And we have then the second term and third term and so on, and then this would be considered the nth term. And our primary focus with a sequence is what is happening with the nth term. And really the question we're going to focus our attention around in this particular section is whether or not the nth term converges or diverges. So whether or not a particular sequence converges to a value or it diverges where there is no pattern at the end. And so we could maybe think back to a sequence that you've possibly heard of, which is the Fibonacci sequence. And that sequence is 1, 1, 2, 3, 5, 8, 11, and so on. That particular formula would be f sub n equal to f sub n minus 1 plus f sub n minus 2. And so that is the formula that would generate this particular sequence. There are obviously many, many, many sequences, and so we'll be looking at all sorts of different types of sequences and whether or not they converge or diverge. So in terms of how we write our sequences, we often will write them in this form of a sub n versus f of n, which is more of that function notation or that function form. So for instance, if you had the function 1 over x and you were looking at just the first quadrant of that, you would see a function that would look like this, and that's how we would write the functions, how we would graph the function. In comparison, if we had a sub n equal to 1 over n, we really are going to have a very similar behavior. However, it's not going to be a continuous function because what we're going to get as we use n as our counter is that we will count this function through, and we would let, for instance, n be 1, and we would get a first term of 1. And then n would be 2, and we would get 1/2, and n would be 3, and we would get 1/3, and 1/4, and so on. Okay, as we were to graph this, we would have a really similar behavior to the function. You would see that similar pattern or that similar kind of curve form, but it would be discrete, where we would have these points rather than this continuous function that would move in either direction. We would have n starting at 1, and then n at 2, and then n at 3, and so on and so forth. In terms of the notation, one of the things that AP will do is they will use this little bracket notation to notate a sequence. And so it's important for you to know that. For example, let's say that you had the sequence n divided by n plus 1, and that was our a sub n, where n was starting at, let's just say 0, and we're going to go to infinity. So if you were to start listing terms here, you would start with n0. That would give you a first term of 0. N would be 1. Your next term would be 1/2. Then n would be 2. You would have 2/3. N would be 3. You'd have 3/4, and then so on. Okay, so in terms of notation, it's just important to know how it looks. Again, this is a sequence. When we start talking about series, you'll see the sigma notation, which we'll get into. Okay, so this is the sequence right now. Here's a definition. We have a sequence that has a limit L, which means that the limit as n goes to infinity of the particular sequence is equal to L. Or we could say that as n gets larger, the sequence approaches a value L. Now, again, I mentioned that our primary focus here with a sequence and as we analyze this is whether or not a sequence converges or diverges. So let's say that we have a particular sequence that maybe looks something like this, where we start graphing all of our terms, and all of a sudden we realize that, this particular sequence is approaching some sort of boundary here that would be L. In other words, when we look at the limit as n gets really large for this particular sequence a sub n, we get a value that it approaches. That's the idea behind a convergent sequence. Now, a divergent sequence would not have that type of behavior. A divergent sequence, which I'll talk about a little bit, is going to maybe alternate. Maybe it's going to just continue to increase indefinitely, and there would not be that limiting value that we could attain. So, for example, let's say that we want to look at. Let's see. Let me erase this. So let's say we want to take a look at. Let's do a sub n equals 1 over n, just something really simple. Okay. If we were to look at the limit as n goes to infinity of this particular sequence, we get 0. And we just know that based on, and don't overthink this. This is just the same type of limits that we've done over the past couple of years here. So 1 divided by a very large positive number is going to be 0. And so what we would say is that this particular sequence, a sub n, is convergent to 0. In contrast, let's say we have a sub n equal to the natural log of n. The limit as n goes to infinity of the natural log of n would be infinity, which means that a sub n is divergent. Or in other words, there isn't a limit or a value L for which the limit as n goes to infinity approaches. And so we have the two contrasts, convergent versus divergent. Okay, if the limit exists, then the sequence converges, which is stated below. Okay, or it's considered convergent. And if the if the sequence does not have a limit there, then the sequence is divergent. Okay, it's a huge concept of this particular section. That's really more or less the goal of this section. Theorem 2, now this theorem is just labeled Theorem 2 because of the textbook, so it doesn't have a formal name, just Theorem 2. It says if the limit as x goes to infinity of a function of x is equal to L, and f of x is a continuous function, and f of n is equal to a sub n, so in other words, the function can be mapped onto a sequence or vice versa, so they can be mapped onto each other. When n is an integer, then the limit as n goes to infinity of the sequence is equal to L. So in other words, it's allowing us to think about a sequence with the mindset of a function. So kind of similar to what I was talking about just a second ago. If we say that f of x is equal to 1 over x, and we want to look at the limit as x goes to infinity of 1 over x, we know the answer to that is 0. And we're thinking in our mind the function. Okay, we're thinking of, and I graphed this earlier, I'll just graph it again. So as x goes to infinity, we can visualize the function and we know the limit is going to be 0. Well, if we look at a sub n equal to 1 over n, we can use this same idea because f of x is a continuous function, f of n is equal to a sub n, where n is an integer, and when we're looking at our graph of this, and we start plotting this out, we can see the behavior is mimicking the function, and we know then that the limit as n goes to infinity of a sub n is also equal to 0. And we can use this theorem to compare these two. Okay, let's move on to the next page. All right, here is a set of limit laws for sequences. Many of them are intuitive, but one of the keys here, and I'll highlight it, is that a sub n and b sub n are convergent. That's why these work. So if you had one that was divergent, so for instance, if you're looking at possibly this very first rule, and let's say a sub n is divergent, but b sub n is not, b sub n is convergent, you cannot apply this rule. You cannot take a divergent sequence and apply it to a convergent sequence and all of a sudden perform one of these properties you have to make sure that both of these sequences involved are convergent. Okay, I'm going to give you a little checklist to add to your notes. And what we'll call it is just a sequence test for convergence or divergence. So if the question says, is the particular sequence convergent or divergent, what I'd like you to do is essentially take the limit. And there's another strategy here as well that I'd like you to try. But if you take the limit initially of the sequence, you sort of have two different situations. So if the limit as n goes to infinity of a sub n is equal to L, then what we can say is then the sequence is convergent to L. And I'll give you examples. I've already given you a couple of them. If the sequence, if the limit as n goes to infinity of a sub n is not equal to L, and I'll give you conditions of that, then a sub n is divergent. Now, what are some conditions for which this is true? Okay, well, what if we had, like, for instance, a non-existent limit? Maybe we had a positive or negative infinity as a result of the limit. Possibly you would have some sort of alternator. For example, you had -1, 1, -1, 1, -1, and so on, where whatever the sequence is, it just alternates forever. There's no real result in the end. And I'll give you some examples of that as well. Any of those cases, what we would say is that the limit as n goes to infinity of the sequence is not equal to a value, and therefore that sequence would be divergent. Okay, so that's what I would like you to do if you are facing the question, is the particular sequence divergent or convergent, is number one, just take the limit and figure out what's happening. Now, there is sort of an informal approach, and I kind of just modeled it there just a second ago, but I'd say maybe an informal test, I suppose. So the limit test is really the one that we're going to use here. Take the limit, see what happens. But another informal test would be to simply just list the terms. Now, you may identify a pattern from that, and I'll show you some examples of this. But if you're struggling to be able to take a limit, if taking a limit is going to be either algebraically difficult, very time consuming, more work than it's really worth, then maybe just list some terms and see what happens. You might be surprised by listing terms. You may see that every term simplifies to 0. Well, that's a pretty clear indicator that the limit's going to be 0. Or you may see that the terms simplify to 1 and then -1 and then 1 and then -1 and so on, and then it's an indicator that it's going to be divergent. And again, I'll give you examples of all this. Okay, a couple more items before we try some examples. We have to talk about the squeeze theorem. This is one that we often will use with sequences or series, and that is that you have 3 different sequences. Okay, you have one that is smaller than the others, you have one that's in the middle of the other 2, and then you have one that's larger than the other 2. And so let's say you have something that looks something like this. So maybe a sub n looks like that, and maybe c sub n looks like this, and b sub n might sort of alternate in between these two, but it's always in between those two. And so if you have the limit of a sub n equal, as n goes to infinity, equal to the limit as n goes to infinity of c sub n, and it's equal to a value, then because b sub n is squeezed between the two, it's sandwiched between the two, it has to have the exact same limit. We use this in situations where b sub n is maybe a little bit abstract. Maybe it's a little bit different than what we can handle. Maybe we cannot do the limit. Maybe we can't list terms. It's just a little bit too bizarre for us to tackle. And so we pick things, a sub n and c sub n, 2 things that are going to be reasonable for us to understand, and we take the limit of those in order to analyze the limit of that one that we just don't quite understand. And again, I'll show you examples of that. Okay, the last theorem before we get into examples is theorem 4. And again, that's just named by our textbook. it says that the limit as n goes to infinity of a sub n is equal to 0 if you take the absolute value of the sequence, then the limit as n goes to infinity of a sub n is equal to 0. This one is a difficult one to grasp without examples, which I will be giving you examples. But you can make a note here that this is a really good one to use when the particular sequence alternates. Okay, so for example, if you have one that goes from a positive to a negative to a positive to a negative, or maybe you have one that goes positive, 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 negative, positive, 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 negative, you can take the absolute value and eliminate all the alternating signs and just look at the sequence as if it was just all positive terms. If, when you do that, it has a limit of 0, then the original also has a limit of 0. And as a visual, it kind of looks like this. So let's say that you have a situation where you end up starting to kind of graph these terms, and you find that they are alternating, but they're getting closer and closer to 0. That's what's going to happen when you take the absolute value of that sequence. And so instead of looking at it alternating, you can actually look at it as all positive terms. And if the limit is 0 given that analysis, then the original has a limit of 0 and therefore is convergent. One thing to keep in mind here is that if you have a limit as n goes to infinity of the absolute value of a particular sequence and it does not equal 0, that does not necessarily mean one thing or the other. So again, this theorem says that if you take the absolute value of a sequence and you get 0, then the original sequence has a limit of 0 and therefore it would be convergent. But if it's not equal to 0, you can't really determine what happens. Okay, for example, let me just give you a quick one here. Let's say that a sub n is equal to 1. That's a really boring sequence, but let's just say that that's what we have. Well, this obviously converges to 1 because the limit of a sub n as n goes to infinity is equal to 1. So this is convergent to 1. If you were to take the limit as n goes to infinity of the absolute value of a sub n, you do not get 0, you get 1. However, sometimes when we read a theorem like this, we think that the opposite tells us something, and it doesn't in this case. We can only take the theorem for the face value of what it's worth right now. Okay, the next video will go through some of our first sets of examples with sequences. Thank you.